So, what we have considered till now is just the converter. So, the converter that we considered consists of actually 6 valves, and of course, if you try to name the converter in terms of the pulse number, I mean what is the pulse number? If you recall, we defined a pulse number, I mean for a general one, yeah, on the DC side. Okay. So, this, I mean one can also define pulse number as the number of pulses that you give to the thyristor valves in one cycle of the AC side waveform. Since there are 6 thyristor valves, if you take one cycle or 360 degrees, the number of gate pulses given is 6. So, it is a 6 pulse converter. So, I do not know whether you are familiar with the term line commutated converter. What is meant by line commutated converter? Yeah, you do not need a special circuit to turn off the thyristor. See, please note, we are not using any special circuit to turn off the thyristor. See, thyristor is a semi-controllable device. That means, you can turn on by giving a control signal. The control signal is in the form of a gate current pulse. So, you can give a control signal to turn on, but there is no possibility of turning off by giving a control signal. So, it will turn off by itself based on the conditions of the power circuit. When the current becomes 0, it turns off. Okay. So, there is no turn off. So, there is no special provision for turning off. So, if you want to forcibly turn off a thyristor valve, you should have some additional circuit, there should be a provision. Now, in this case, there is no such provision. So, whatever happens for the thyristor valve is based on the power circuit. So, that is a line side. So, that is why it is called the line commutated converter. Okay. So, we say that the converter that we considered till now is a 6 pulse line commutated converter with AC side represented by just a voltage source. Okay. So, that is a 6 pulse line commutated converter. So, many times this line commutated converter is abbreviated as LCC. So, we have just analyzed line commutated converter, which of course, a 6 pulse line commutated converter with a simplification of the inductance on the AC side to be 0. Okay. Now, that is just for the sake of simplification. In reality, there will be an inductance on the AC side, because the AC side cannot be just represented by a voltage source. This voltage source is nothing but the EMF induced in a transformer, and a transformer invariably has a leakage inductance. So, some leakage inductance will be invariably there. So, the AC side representation should have inductance. Okay. So, now we will see how to analyze a slightly complicated circuit, where in addition to voltage source on the AC side, there is an inductance in each phase. So, let us consider this circuit. Of course, I have a converter with 3 legs. The DC side is represented by a constant current source ID. On the AC side, I have a 3-phase voltage source connected in Y or star. And in each phase on the AC side, there is an inductance. The inductances in the 3 phases are identical. So, let L be the inductance. So, the voltage in phase A is EA, in phase B it is EB, and phase C it is EC. Of course, we will be using the same expressions for EA, EB, EC, the ones which we have been using for the previous case. Root 2 by 3V sine omega OT plus 150 degrees, that is EA. EB is root 2 by 3 V sine omega OT plus 30 degrees. And EC is root 2 by 3 V sine omega OT minus 90 degrees. So, the thyristor valves are named as 1, 3, 5 for the upper commutation group, and for the lower commutation group it is 4, 6, 2. So, the only difference is now there is an L, the previous case L was 0. So, what is the change that one can expect due to the presence of the inductance on the AC side?
Sudden changes in the current that you were.
Yeah, there was a discontinuity in the current. See, if you look at the current through the voltage source or current through the valve, there was it can go from ID to 0, 0 to ID, the valve current. But now that sudden changes in the current through the source cannot happen. So, what does that mean? So, let us see. Suppose one is thyristor valve 1 is conducting, thyristor valve 2 is conducting. Okay. Now, if I turn on, the next valve to be turned on is 3. So, if L is 0, whatever ID on the DC side that was flowing through 1 will instantaneously shift to 3. So, we say there is a transfer of current from valve 1 to valve 3 as soon as valve 3 is turned on. So, this process of transfer of current is called commutation. I defined this word commutation. Commutation means the transfer of current from one valve to another in the same commutation group. Now, can it happen if L is non-zero? Say, transfer of current from valve 1 to valve 3 actually means transfer of current from the inductance L in phase A to inductance L in phase B. So, suddenly the current through the inductance cannot go from ID to 0 in phase A and 0 to ID in phase B. So, it will take some non-zero time for current to go from ID to 0 in phase A, 0 to ID in phase B. Similarly, the same currents are flowing through the valves. So, the current through the valve cannot suddenly go from ID to 0 or 0 to ID. Okay. So, what I mean to say is, so let me just state that here. Current through a thyristor valve can vary only at a finite rate. So, that means if you take the rate of change of current with respect to time, of course. So, in the previous case it was infinite. So, the discontinuity in the current means the rate of change is infinite. Now, that is not possible with a non-zero value of the inductance. So, this is as good as saying a commutation from one valve to another, commutation from one valve to another. So, we already defined this word commutation. Commutation means transfer of current, transfer of current from one valve to another takes some time. So, just now I said, suppose valve 1 and valve 2 are conducting. If valve 3 is turned on, current won't get transferred to valve 3 immediately. So, it takes some time. That means, there is a certain duration for which both valve 1 and valve 3 are conducting. Now, this is different from the previous case where at any time if you take any basic commutation group, only one of the valves conduct at any instant. Now, we have a situation where there are some instants at which two valves conduct. Okay. So, for a certain duration both 1 and 3 conduct. Of course, after some time 1 stops conducting, again only 3 alone will be conducting from the basic commutation group consisting of 135. Okay. So, what we do now is we try to define a duration for which both valves conduct. Okay. So, we will give a name for that, that is known as overlap angle or commutation angle. Overlap angle or commutation angle. So, we use the letter U for this, the notation is U. So, let us see how to define this. So, the definition is simple. I take the duration, of course, I always measure the duration in terms of angle, not in terms of time, or independent variables angle. Duration for which each valve conducts in one cycle. Say our cycle is the cycle of the AC side, minus what? Say I have to subtract something from the duration for which each valve conducts in one cycle, that gives me the overlap angle. Now, what I mean is, suppose L is 0, there is no overlap. See, overlap means there is no duration for which two valves conduct. Okay. So, U or overlap angle or commutation angle is 0 if L is 0. If L is non-zero, there is a non-zero U. So, what should I subtract from this duration to get U?
That time for which only.
Yeah, what is that? If L is 0, what is the duration for which each valve conducts? Yes, 120, it is 120. So, now it is more than 120. So, do you remember this? We when there is no inductance on the AC side, each valve conducts for just 120 degrees exactly in one cycle. So, there is a 120 degree duration. Now, it is more than 120. So, the difference between the duration and 120 is the overlap angle. Okay. So, that is the definition of U. Okay. So, U is the notation used for overlap angle or commutation angle.